Chapter 2, Module 2. In this module, we shall discuss cardinal numbers. Cardinal number relates to the size of a set. We wish to find whether a given set has same number of elements with another set. Now, when we are saying that same number of elements, we mean that the set is finite. But in case of infinite sets, how do we say that? In that case, we cannot count the number of elements. So, we want to pair off each element of one set with another element of the other set. For that matter, we want to introduce equipotents of sets. Two sets A and B are said to be equipotent or equivalent if there exists a bijective map from A to B. If S denotes the class of all sets, then define a relation on S as follows: A is related to B if and only if A is equipotent to B. This relation on S is an equivalence relation on the class S. Why it is equivalence? It is reflexive, it is symmetric, and it is transitive. It is reflexive because the identity function I from A to A is a bijection. It is symmetric because if F is a bijection from A to B, then F inverse from B to A is also a bijection. So, B is related to A. It is transitive because A related to B means there exists a bijective function F from A to B. B related to C means there exists a bijective function G from B to C, so that the composite G composed F is a bijective function from A to C, which proves A is related to C. We observe that if A is an empty set, then empty set is always related to itself. If we take Jn as a set consisting of finitely many integers 1 to n, then Jn is related to Jm if and only if m is equal to n. Now, see, if m is equal to n, then it is clear that Jn should be related to Jm. On the other hand, if Jn is related to Jm, then there exists a bijection F from Jn to Jm, which in turn gives that the number of elements in Jn is equal to the number of elements in Jm. So, n is equal to m. Denote the equivalence class of A under this equivalence relation of equipotents by mod A. We observe that if Px stands for the power set of x and 2 to the power x stands for the collection of all functions from x to the set 0 1, then mod Px is equal to mod 2 to the power x. That means, the power set of x and the set 2 to the power of x are equipotent. Why? Because if we take any subset A of x, we can always write the characteristic function chi A of that particular set A as usual, that is characteristic function of x is 1 when the point x is taken from A, and it is 0 if x is not in A. Defining the function psi from Px to 2 to the power x by sending the set A to its characteristic function chi A gives us a bijection, thereby showing that Px is equipotent to 2 to the power x. For two sets x and y, we now define a relation less than equal to among the class x and class y as follows. We write that mod x is less than equal to mod y if there is an injection from x to y. We write that mod x is strictly less than mod y if mod x is less than equal to mod y and x is not equipotent to y. The following are easy consequences. For any subset A of x, mod A is less than equal to mod x. This happens because we have the inclusion map I from A to x, and we know that inclusion map is an injective map. And if there exists a surjective function f from x to y, then mod y is less than equal to mod x. This happens because if we take the collection f inverse y, where y varies over the set capital Y, then this collection forms a partition of the given set capital X. We choose the choice function C for the family power set of x, then defining a map from y to x, sending the element y to the element C of f inverse y gives us an injection which shows that mod y is less than equal to mod x. Next is a very important one. Here in this theorem, we see that any set A, if we take, then mod A should be always less than mod of power set of A. The assignment A goes to singleton A defines an injective map from A to power set of A. So, mod A is less than equal to mod of power set of A. For if there is a bijection f from A to power set of A, then there exists some A belonging to capital A such that f A, which is the set containing all the points B from capital A such that B is not in f B, will be a subset of A. But that is definitely a contradiction, because the point A is in B and the construction of the set f A says that the point is not in B, and this contradiction says that such bijection is not possible, thereby proving the inequality to be strict. It is known that an equivalence relation always partitions a collection into disjoint equivalence classes. So, this particular equivalence relation of equipotents also partitions the collection of all sets into disjoint equivalence classes. If we take any set capital A, then that particular set is inside exactly one such equivalence class. So, we could have defined cardinal numbers as the equivalence class in which the set lies, but unfortunately these equivalence classes are not necessarily sets. So, if we associate an equivalence class as an object and we call it a cardinal number of the set A in which that set lies, then that will no more be in the framework of set theory. To get rid of this difficulty, we introduce the notion of ordinal numbers and then define cardinal numbers in terms of ordinals. A set A with respect to a binary relation less is called a partially ordered set if this relation is reflexive, transitive and antisymmetric. A partially ordered set A is called a well ordered set if for each non-empty subset B of A there exists some B0 belonging to capital B such that B0 is less than B for all B belonging to B, and such an element B0 is called a first element or least element of the set B. Zermelo's theorem says that every set can be well ordered. Now, we introduce two more concepts. W is any well ordered set. A subset of W is called an ideal of W if for all x, x belongs to A and y less than x implies that y belongs to A. For each A belonging to W, the set W A, which is the collection of all x belonging to W such that x is less A and x is not equal to A, then this W A is called initial interval determined by A. Clearly, empty set and W both are ideals in W, but empty set is an initial interval though W is not. The ideals which are not equal to W are initial intervals. Now, suppose we have two well ordered sets W less and W1 less 1. A map F from W to W1 is called a monomorphism if it is an order preserving injective map. It is an isomorphism if it is a bijective monomorphism, and it can be observed very easily that composition of two monomorphisms is a monomorphism. If F from W to W1 is an order preserving bijection and if W is well ordered, then the order in W1 is also a well order and F is an isomorphism. In the next theorem, we see how the ordinals are compared. If two ordinals are taken, one is capital X and the other one is capital Y, then one and only one of the following can hold. The first one says that there is a unique isomorphism of X onto Y. Second one says that there is a unique isomorphism of X onto an initial interval of Y. And the third one is there is a unique isomorphism of y onto an initial interval of x. The following is an important consequence of this result. It says that any subset A of a well ordered set W is isomorphic either to W or to an initial interval of W. In the class of all ordinals, we define a relation that W1 relates to W2 if and only if W1 is isomorphic to W2. This relation is an equivalence relation on the class of all ordinals. So, by means of this equivalence relation, the class of all ordinals are partitioned into disjoint equivalence classes. With this knowledge, we define an ordinal number as follows. An ordinal number is a set alpha satisfying two properties. Number 1, x belongs to alpha and y belongs to alpha implies that x belongs to y or y belongs to x or they are same, that means x is equal to y. Number 2, x belongs to y and y belongs to alpha implies that x should be inside alpha. One can prove that if L is the class of all ordinal numbers and if we define less than equal to on this class L as inclusion of sets, that means alpha less than equal to beta if and only if alpha subset of beta, then L is well ordered by this relation less than equal. For each alpha belonging to L, the initial interval L alpha is equal to alpha. In particular, L alpha is a set. Each well ordered set W is isomorphic to a suitable L alpha. Alpha is called the ordinal number of the well ordered set W and we denote it by odd W. We state a fact without proof which we require in our course. The fact is, one can think of this L as a well ordered class of well ordered sets containing exactly one representative from each equivalence class of isomorphic ordinals. With this much knowledge of ordinals and ordinal numbers, we proceed to introduce cardinal number of a set. Now, let us once again think what we want to do. Our objective is to assign a symbol to each set capital X called cardinal number of X, so that two sets have the same cardinal number if and only if they are equipotent. For that matter, we see that every set in a equipotence class can be well ordered. Since any well ordered set is isomorphic to a suitable L alpha and L is well ordered, each equipotence class contains a smallest such ordinal number. This uniquely determined representative is called the initial ordinal number of the equipotence class. Now, we define the cardinal number of a set X as the initial ordinal number of its equipotence class, and we denote the cardinal number of the set X by aleph X. So, the cardinal number is an ordinal number that is not equipotent to any smaller ordinal number. We use these following notations: aleph empty set is equal to 0, that means cardinal number of empty set is 0. Cardinal number of a finite set 1 to n is n, that means the number of elements of the set coincides with the cardinal number of the set for a finite set. Aleph of the set of natural numbers is denoted by aleph naught, that means the cardinal number of natural numbers is aleph naught, and cardinal number of the real numbers is denoted by C. A cardinal number is called transfinite if aleph x is not of the form n for some n. A set is finite if its cardinal number is n for some n belonging to natural numbers. A set is countably infinite if the cardinal number of x is aleph naught. A set is uncountable if cardinal number of x is neither n nor aleph naught. Let us define a relation less than equal to for the cardinal numbers. Aleph x is less than equal to aleph y if aleph x is isomorphic to an ideal of aleph y. In the next theorem, we see that mod x less than equal to mod y if and only if aleph x is less than equal to aleph y. In particular, two sets are equipotent, that means mod x is equal to mod y if and only if they have the same cardinal number. Since x is equipotent to aleph x, there is a bijection from x to aleph x. On the other hand, aleph x is less than equal to aleph y implies that there is an isomorphism from aleph x to some ideal of aleph y, and therefore, an injection from aleph x to aleph y. Again, equipotence of y with aleph y gives a bijection from aleph y to y. So, composing all these, we get an injection from x to y, proving that mod x is less than equal to mod y. Conversely, let the cardinal number of x is less than equal to cardinal number of y. By equipotence and using the definition of less than equal to, there exists an injective map from x to aleph y. Regarding x as a subset of aleph y, we then have that x is isomorphic to aleph y or an initial interval of aleph y. So, ordinal number of x is less than equal to aleph y. Since aleph x is less than equal to ordinal of x is always true, we get that aleph x is less than equal to aleph y, which was desired. As a consequence of this result, we have a very well known theorem called Schroeder-Bernstein's theorem. It says that if x and y are sets such that mod x is less than equal to mod y and mod y is less than equal to mod x, then mod x should be equal to mod y. That means, if there exists an injection from x to y and an injection from y to x, then we must have that the given two sets x and y are equipotent. By the last theorem, mod x less than equal to mod y implies that aleph x less than equal to aleph y, and mod y less than equal to mod x will imply aleph y less than equal to aleph x. According to the theorem on comparability of ordinals, aleph x is less than equal to aleph y and aleph y less than equal to aleph x will imply that aleph x is equal to aleph y. Consequently, we have from the last result that mod x is equal to mod y. In view of the last theorem, we may restate in terms of cardinality the theorems that we have proved for equipotent sets. Cardinality of A is strictly less than the cardinality of its power set. That means, there is no largest cardinal number. And another one is that the cardinality of any finite set is the number of elements of the set, and therefore, 0 is the smallest cardinal number. Finally, before we conclude, we state what is known as continuum hypothesis. It says that there is no cardinal number between the cardinality of the natural numbers and the cardinality of real numbers. In view of the last result, that cardinality of a set X is strictly less than the cardinality of its power set, one may ask a question that does there exist any cardinal number between these two? The hypothesis that there is no such cardinal number is termed as the generalized continuum hypothesis. One may discuss cardinal arithmetic by introducing addition and multiplication on cardinal numbers. For the details of these kind of results relating to cardinal arithmetic, one may refer to the e-content of this course. And with this, we end chapter 2 and thereby completing our course on set theory.